Alright, so now we're going to talk about stoichiometry. And stoichiometry is really a big deal in chemistry. It's kind of one of the big topics that we talk about. It sounds a lot confusing, a lot more confusing than what it is. It's really cooking, honestly. So the main idea is the amount of each reactant starting the chemical reaction determines how much you're going to get at the end. So if you're making, chocolate chip cookies and you have half a bag of chocolate chips, then you're not going to be able to make the entire batch of chocolate chip cookies according to the recipe. Same idea here. The amount of each reactant you have determines how much product you're going to get at the end. Okay, and chemical reactions stop when one of the reactants are used up. So if you've watched a candle burn out, when the wax is gone, it stops burning and the combustion reaction ends. If you're trying to make chocolate chip cookies and you run out of chocolate chips, well then you got no more chocolate chip cookies. So it's pretty much that simple. So, definition of stoichiometry is very technical. This is a study of quantitative relations between the amounts of reactants used and the amounts of products formed by a chemical reaction. It's basically what it means is how much you start with determines how much you get at the end. It's really what that comes down to. It's based on the law of conservation of mass, that the amount of matter that you start with has to equal the amount of matter at the end. And you can't just suddenly create it. So, for example, in a stoichiometry, first thing you have to do is have balanced equations. So if I was to balance this, I would put a 3 here. This is 3 carbons. I'd put a 4 here. I have a total of 10 oxygens, so I need a 5. Okay. Coefficients indicate that it takes 1 C3H8 to react with 5 oxygen molecules to form 3 CO2s and 4 waters. That's what the coefficients tell you. They also tell you the number of moles of each chemical. So if I was talking about 1 molecule and 5 molecules and 3 molecules and 4 molecules, if I was talking in terms of a large scale, something that I could count, it would be 1 mole and 5 moles and 3 moles and 4 moles. Because everything multiplies to go from molecules to moles, all you need is Avogadro's number to make that change. So if you could determine the total mass of all the reactants and compared to the total mass of all the products, the total masses will be equal to each other because you cannot create or destroy atoms. They cannot be done. So what we're going to talk about first, we're going to talk about something called mole ratios. And so we're going to be setting up a proportion here. And most people tend to freak out with proportions. It's not as hard as you think to do this, but it tends to be a little bit confusing to people sometimes. So the coefficients in a chemical equation indicate the relationship between the number of moles, not just the number of atoms or molecules. And the mole ratio is a proportion between the number of moles of any of the substance as long as the equation is balanced. That's got to be the first thing that's done. So for example, in this relationship, balanced chemical equation, the mole ratios of K to KBr are a ratio of 2 to 2. It takes 2 Ks to make 2 KBrs. And for KBr to Br2, it's 2 KBrs to 1 Br2. Remember, that's understood to be a 1. And for Br2 to K, it's 1 to 2. And all I did was use the coefficients from the balanced equation to set up those ratios. So the solution to every stoichiometric problem requires the balanced chemical equation first. Okay, so you guys have been practicing that for quite a while. Mole ratios are conversion factors that convert between the starting number of moles and what you're trying to solve for, the number of moles. And that's all it is. It's just a little conversion. So you're starting with moles of one chemical. You're going to multiply by the ratio of that chemical, we're going to call it A, change it into a different chemical, and you're going to use the coefficient from that balanced equation. That's why the very first step has to be balanced. This will cancel out, and you're left with moles of your unknown. Okay? I want this to go away. There we go. All right, so using the balanced chemical equation for the combustion of C3H8, so we had C3H8 plus 5 oxygens goes to 3 CO2s and 4 waters. What are the mole ratios of C3H8 to CO2? Well, 1 C3H8, 3 carbon dioxides. Oxygen to water, 5 oxygens to 4 waters. And it's just that simple. So, how many moles of CO2 are produced when you start with 10 moles of propane? So start by writing down your unit, number and unit, and it's very helpful to write the chemical. Then put the chemical on the bottom. You don't necessarily need to put the unit on the bottom, but you're going to put the chemical on the bottom because at the end you want moles, but you want to put the chemical on the bottom, and then you want to change it into whatever chemical they're asking about is CO2. And so what I'm going to do is I'm going to look back at my balanced equation, and I'm going to write down the coefficients in this mole ratio. C3H8 has a coefficient of 1. CO2 has a coefficient of 3. So I'm going to take those numbers and multiply, and I'll get 30 moles of CO2. When it comes to sig figs, these guys are considered infinite because they are counting. It's counting atoms. It's counting moles. So they don't count for sig figs. This counts for sig figs and my answer. And so C3H8 cancels out, and I carry 10 times 3 moles of CO2. Okay, so that's how you use a mole ratio. Oops, let me erase everything on the slide because that makes no sense. So, how many moles of oxygen are used when you start with 0.525 moles H2O? And again, I'm going to put my H2O on the bottom because I want to get rid of it, and I'm turning it into moles of oxygen. So I'm going back to my balanced equation. There were 5 oxygens and 4 waters. Water cancels out. So I've got 0.525 multiplied by 5 divided by 4. Or divided by 4 and then multiplied by 5, and you get 0.656. And again, moles, because that carries through, but this time it's moles of oxygen. And that's how you use your mole ratios, is they come straight from the balanced equation. Okay, so for this one, different balanced equation. Calculate the moles of CS2 produced when 1.5 moles of S8 are used. Okay, so now, what you want to do, start by 1.50 moles of S8. So go ahead and pause the movie, see if you can come up with this one. Keeping in mind you're going to use a mole ratio, you want to change from S8 into CS2. Okay, so if you use the balanced chemical equation, 1S8, 2S2, or 2CS2, you get 3.0 moles. The S8 cancels out, and you're left with CS2. Okay, I'm going to erase the ink again. Okay, go ahead and see if you can do this one. 0.75 moles of CS2. CS2 on the bottom, H2S on top. Again, I'm starting with this, and I want to solve for that. CS2 cancels out. It's got a coefficient of 2. H2S has a coefficient of 4. And you end up with 1.5 moles of H2S. Okay, and that's how you use mole ratios. It converts between one chemical to another chemical. That's what it's used for. Now, when we start throwing grams at you, we can't measure how many moles we have of something directly. It's not like I can say, oh yeah, look, here's my collection of CS2, and that's 5 moles. No way of knowing that. So what we have to use is we have to use grams, which means we need to be able to convert between grams and moles before we do the mole ratio. So you want to just pay attention to the units and the chemicals when you're doing this. So here's a balanced chemical equation. Sorry, not balanced. Needs to be balanced. Put a 2 here and a 3 there. So I'm going to pay really close attention to what I'm starting with. I'm starting with 25 grams of N2. In order to use my mole ratio to change from N2 into NH3 using that mole ratio, this has to be moles first. So I'm going to put grams in the bottom, moles on top. We learned how to do this in Chapter 8. I always put a 1 by the word mole. And then I look up nitrogen. It's 28 grams. Grams cancels out. And then here's where I'm going to do my mole ratio. N2 on the bottom to cancel out, and NH3 on top. Mole ratios change from one chemical to another chemical based on the balanced equation. So I have 25 divided by 28 and then multiply by 2. And I get 1.79 moles of NH3. Okay, 3 sig figs because 3 sig figs and 3 sig figs. And again, this doesn't count. But that's what you want to watch out for. If you're starting with grams, first thing you have to do is change it to moles. Then you can do this mole ratio, which changes from one chemical to the next. Oh, heavens. All right, racing. All right, let's try this one. So you're starting with 5.75 grams of hydrogen. And again, I'm trying to change from hydrogen into NH3. I can't do that from grams. First, I have to change from grams into moles. And hydrogen on the periodic table is 2. Grams cancels out. Once it's in moles, then I can put my hydrogen on the bottom and the NH3 on top. This had a 3, that had a 2. Hydrogen cancels out. And I got 1.92. Actually, it should be 1.9 moles of NH3. 2 sig figs because of that. So you just have to pay close attention to your units. Your mole ratio only works when you're going from moles of one thing into moles of something else. Okay, so same equation, 3 and 2. So pay attention to what your units are. You're starting with 0.753 moles of NH3. If you are in moles, you can change from moles of one thing to moles of the next right away. You don't have to change it into grams. Moles does everything. So it takes NH3 on the bottom, hydrogen on top, 2 NH3, 3 hydrogens. NH3 cancels out. But I want grams of hydrogen. So I'm going to take it one more step. 1 mole of hydrogen is 2.0 grams. Moles cancels out. And so all I'm going to do is multiply 0.753 times 3 divided by 2 times 2. And I get 2.26 grams of hydrogen. But again, this step, this mole ratio, that's what makes it stoichiometry. And it has to go from moles of one thing to moles of something else. If it involves grams, that's a conversion like what we did in the last chapter. Okay? So go ahead and see if you can do this one. Pay attention to what you're starting with, 1.95 moles of hydrogen. And if you are in moles, moles does everything. I can change right away from moles of hydrogen into moles of something else. This is a 3 and a 2. So hydrogen on the bottom, nitrogen on top, put a 3 and a 1. Hydrogens are gone. But I want grams, which means I need to take this one more step. 1 mole of nitrogen is 28 grams of nitrogen. And so the moles end up canceling out, and I end up getting grams. So 1.95 divided by 3 times 28, I got 18.2 grams. So pay attention to units. That's the biggest thing you can do. Always have a balanced equation first. Start by writing down the number, the unit, and the chemical. If it's not given as moles, convert it to moles first, using what we know about moles. Then convert from moles of what you want, convert it to moles of what you want using the mole ratio. You may not skip this step. This is what makes it stoichiometry. And then, if they want something other than moles in the desired unit, say they want grams, you convert to that. Okay, and so this is kind of the setup. It should have like equals grams of B written right there, but it's hard to squeeze it in. If you are starting with grams, you're going to put grams on the bottom, 1 mole on top. This is the mole ratio from the balanced equation. This step must happen every single time you are changing from one chemical to another. And these are the coefficients that they have. And then if they want grams of B, 1 mole of B, molar mass right off the periodic table. These guys come off the periodic table. This one comes from the balanced equation.